I hope everyone is ready for some interesting abstract algebra that may redefine how you learn basic arithmetic as a child. So let's get started. So let's start considering how to become more professional scientists, mathematicians, and engineers. In this lecture, I plan to introduce some of the mathematical encapsulating structures that allow us to analyze elements of a set. We will be introducing a set along with operations with very specific properties that define how elements on a set interact with each other. Take a look at the image I grabbed from the Wikipedia page associated with the topic we'll be discussing shortly. As you can see, the relationships can be quite complex. It's important that you understand how the objects extend each other rather than simply trying to memorize the individual components of each mathematical object listed. Now, to be clear, we will not be covering all the objects on this image, but we will be covering most of the common ones. A set by itself is just a collection of elements. When we define an operation on that set, we are describing how two elements can be combined to create another element. For the operation to make sense, the result must also be an element of the set. This property is called closure. For example, if we take the integers under addition, adding two integers will always result in another integer. So imagine this like your group of friends. Whenever one friend shares something with another friend, it stays within the group. That's kind of effectively what we're saying right now. Whenever you take two elements of a set and you apply the operation that has been defined, the result should be another element inside the set. That is what we're referring to when we say the closure property. In computer science, it's important to think about the distinction between has a and is a when determining relationships. A set has elements, an operation has rules. When we combine them, we create a structure that is defined by both. The difference between having and being is key to abstraction layers in computer science. So imagine that we create a class called vehicle. A Ford truck is a vehicle. And so we'd say the Ford truck class extends the vehicle class. However, a Ford truck has an engine, but the Ford truck nor the engine extend each other. That's the difference between has a and is a relationship. A magma is the simplest algebraic structure of this kind. It is simply a set together with a binary operation. You can think of it as encapsulation. The magma has a set and it has an operation. The only requirement of magma is that the operation be closed. For example, the integers under addition form a magma. The even numbers. Anytime you have an even number, you take another even number and you add them together with traditional addition, you get another even number. So the even numbers are also a magma. However, take the set of odd numbers under the addition operation. Taking two odd numbers, adding them together will give you an even number. So the odd numbers do not form a magma. A semigroup is another abstract encapsulation device that sits between a magma and a monoid. It has a set and a binary operation like a magma, and it also requires that the operation be associative on the set. So to be clear, a semigroup extends a magma. So effectively, to have a semigroup, you take a magma, but you also require it to have associativity on the operation. That means the way you parenthesize does not matter. First combine x and y and then z, or combine y and z first and the result is the same. There is no identity element required for a semigroup. Floating point arithmetic is not associative as an example. Subtraction is not associative as an example. A monoid is the next step in our examples of extending mathematical objects to create new ones. A monoid is a special case of a semigroup. You can think of it as extending a semigroup. It has all the properties of a semigroup except that it adds the requirement that there must be an identity element. A monoid, it is a semigroup, and by extension, it's also a magma, but with extra structure. So recall, the magma, that's where we got closure. Then we extended it. The semigroup, that's where we got the associative property requirement. And now we're adding the requirement that we have an identity element. An identity element, think of that as kind of being the 0 under addition or the 1 under multiplication. Anytime you add a number to 0, you get that number back. Anytime you multiply a number by 1, you get that number back. So the whole numbers under addition form a monoid. The set of natural numbers do not, because the identity element 0 is not part of it under traditional arithmetic. So let's summarize the hierarchy that we've described. First, we have a set, and then we require an operation that will operate on those elements inside the set. We encapsulate those two things together, the set with its operation, and we have a magma. It's just a mathematical encapsulation tool that we use, and then we extend it. A semigroup is a magma that also satisfies associativity. A monoid, it's a semigroup that also has an identity element. So a monoid is a semigroup, and a semigroup is a magma. So from an object-oriented perspective, for those of you guys that enjoy C++, Java, or Python, you can imagine monoid extending semigroup, and semigroup extends magma. I know that I've been quite repetitive on this, but the more you train your mind to think of these in an extension or is a type relationship, the more mature you'll become as a mathematician and the more mature you'll become as a software developer. Here are a few quick examples to contrast the levels. Integers with subtraction form a magma because subtraction is closed. Anytime you subtract two integers, you get another integer. But it is not associative, so it matters on how you group things together. So if it's not associative, it cannot be a semigroup. And if it's not a semigroup, it's certainly not a monoid. Positive integers under addition form a semigroup because addition is associative and it is closed, forming the magma, but there is no identity inside the positive integers. The positive integers have no additive identity, so it's not a monoid. Missing the identity prevents it from being a monoid. Natural numbers under addition form a monoid if we add the number 0. So the set of whole numbers under addition form a monoid. Also, strings under concatenation form a monoid with the empty string as the identity, to provide a little bit of a more abstract and less concrete example. Let's revisit, just to make sure we understand, the computer science perspective of all this. A magma has a set and an operation, and we're emphasizing encapsulation, which is commonly referred to in object-oriented languages. A semigroup is a magma with the addition of the associativity requirement. A monoid is a semigroup with an identity element. Thinking in these layers helps you design abstraction layers and reason about which algebraic guarantees your code can rely on. It will also help you develop code in a more modular fashion, and at some point you'll become such a mature developer that you'll be writing code that becomes modular and plugs in nicely with other code without you having to go through abnormal amounts of effort to create those structures. Let me take a moment to go to my notebook and let me give you some examples and explain the examples as we go through. So let's start from the beginning. Let's provide some concrete examples for the things that we've discussed. First, let's go over what it means for closure. Okay, let's suppose that we consider the set of natural numbers. And let's define the operation to be just traditional addition. So I'll use the plus sign. Now when I start creating these operations to be more complex and less abstract, or more abstract and less familiar, then I can start using my own symbols. I can even use the heart symbol or whatever else. But for right now, since I'm relying on traditional arithmetic, let's just keep the traditional plus sign as our operation symbol. Okay, now at some point we're going to be talking about something so trivial that it's almost axiomatic, something that doesn't need a proof. So imagine a natural number, and recall the natural numbers is this set of numbers, 1, 2, 3, ... Okay, now when we have the set of natural numbers, notice that if you pick a natural number and you pick another natural number and you add them together, you always get another natural number. So what this means is the natural numbers, I'll abbreviate that, called the naturals, are closed under traditional addition. And remember, we can redefine this operation to be something less familiar, but for now we're saying it's closed under traditional arithmetic. Now let's look at the set of natural numbers, and so by the way, we have closure here. So let's look at the natural numbers and let's add subtraction to it. Now, whenever we say something is closed, whenever we say something is closed, that means that any two arbitrary elements that we pick and you add them together, you perform that operation on them, you have to get another element in the set. That must be true for every single element. Every single pair of elements, the operation on them has to result in another element inside the set. To represent that mathematically, here's what I'm going to do. A plus B equals C, and C has to be in the set of natural numbers for all A and B in the set of natural numbers. Okay, now that could be a little bit hard to digest. Take a look at what I just said out loud here and what I wrote. What I'm writing is much more condensed than what I just said out loud. So let's read this mathematical statement together. A plus B equals C has to be a natural number for all A and B in the naturals. Let's restate that to something a little less concise. Pick any two values from the natural numbers. Add them together, you'll get another natural number. That means the set is closed under this operation. Okay, now typically this is such a simple example that it'd almost be difficult to even prove it, since the natural numbers are kind of our starting point at everything. And let's just take my word on it for right now, okay? Because I'm afraid that I'll muddy up the water by trying to give some sort of exhaustive proof on this when it's so simple to begin with. But let's now consider the negative, so our subtraction. So the natural numbers under subtraction are not closed. Why? Remember, all it takes is one violation to make the whole set not closed. So what if we have an infinite set and everything works out except for two pair of numbers that do not result in another element of the set? This happens a lot, and it's kind of an edge case like we talk about in computer science, and sometimes it can be difficult to identify. But let's say this out loud. It only takes one pair of values that does not result, under the operation, that does not result in another element of the set to violate closure. So it has to be for all arbitrary pairs resulting in another element inside the set. So if all we have to do is just show one hiccup and then say that it's not closed, we do that by counterexample. So let me show you a counterexample that shows the natural numbers are not closed under subtraction. Take the number 3 and subtract 5, and you get what? -2. -2 is not in the set of natural numbers, but 3 and 5 are in the set of natural numbers. And so what we must say is that the naturals are not closed under subtraction. The naturals are not closed under subtraction. Okay, so we got our first two really trivial examples under our belt, and now let's move on. Since we understand what closure may mean, let's do one more example and a counterexample, and let's see what we're talking about. So let's define the set of even numbers to be the set of numbers 2k such that k is a whole number. So what that is in roster form, that's 0, 2, 4, 6, 8, ... Okay, now if I'm going to say that the operation is traditional addition, so I'm going to take the set and then I'm going to add addition. This is a magma, but I have to prove that it's a magma. Why is it a magma? Because for one, we have a set, the operation is well defined on this set, and we have to show that there's closure. So closure means that anytime we take two elements from the set and we add them together, the result will be another element in the set. Now we're doing addition as a very specific example here, so we could define that operation to be anything, but we're doing traditional addition to keep things simple. So we have the set of even numbers, and under addition they form a magma. But I need to prove that. I'm going to have to get beyond just stating things are true, because it can be a little bit clumsy and I may not recognize the edge cases. So I need to provide an argument that will show that this is true for any pairwise elements from the set of even numbers. All right, well, the way that I can prove that is I could use the definition of an even number, and I could basically say I'm going to take two arbitrary values and I'm going to prove that the result will be another even number. And since I did not actually give a definite definition for those two arbitrary values, it must be the case that it must hold true in general. thus making it true for the entire set. So let's get started with that. Let's suppose that I'm going to pick number 1, even number 1, and I'm going to say that whatever it is, we're not picking a specific value, but I can define it to be, by definition, 2k, where I'll do this k sub 1. And then n sub 2 will be 2k sub 2. And what we're going to say is k1 and k2 are some values in the whole numbers. So basically what I'm doing is I'm saying let n1 be an element of the set. Let n2 be an element of the set. Represent n1 and n2 by the way elements are defined in the set. In other words, 2 times some whole number. Well, that means k1 must be a whole number, k2 is a whole number. So we're good. So we're basically claiming that n1 and n2 are elements of E. Great. Okay, now what I have to show is that n1 plus n2 will be another element in set E. So let's get started with that. So I'm going to say n1 plus n2. And I'm going to say that that will be the same thing as saying 2k1 plus 2k2, since that's how I defined it. But notice that I can factor out the 2. I can factor out the 2, and then we have k1 plus k2. Now notice that k1 and k2 are from the set of whole numbers. And what can we say about the whole numbers? They are closed under addition. That means if you add 2 whole numbers, you'll get another whole number back. So we can determine that the sum of these 2 whole numbers must be another whole number k in the set of whole numbers. Now, to be clear, I needed to have 2 distinct whole numbers. So that's the reason I said k sub 1, k sub 2. But now what I'm doing is I'm making a broad statement that says when you add k1 and k2, we don't actually care what the value is because we're just showing this in general to be true. That means we could just represent their sum as k, and we know k must be a whole number. So at this point, we know that we have 2 times k, where k is a whole number, and that must mean that this is even because an even number is just simply 2 times a whole number. So that means that 2k is in the set of even numbers. And that must mean that n1 plus n2 is in the set of even numbers. Okay, and that's great. Whenever a mathematician finishes a proof, here's sometimes what will happen. The mathematician will draw a little box and color it in, and that signals that the proof is finished. Other times, a mathematician may write the 3 letters QED. QED is essentially an abbreviation for a Latin phrase. To paraphrase, it means I've shown what was required. So you guys can look it up. Every time I look up what this phrase actually is, I forget it, but I do remember what QED is. And every time I look up what the phrase translates to, I always see something slightly different. But the gist is, this is an abbreviation for a Latin phrase that means I've shown what was necessary to finish my proof. Okay? So what have I just shown? That E, comma, plus, so what do we have? We have a set, we have an operation on the set, and together it is closed. Sorry, I wrote off the screen a little bit. It is closed. And so if we have a set and there's an operation, we encapsulate them into one structure, and if that holds with closure, then we refer to it as a magma. So all of this is a magma. Good. Now let's look and see. Sometimes all we have to do is just find where one counterexample happens. Let's suppose we define the odd numbers to be the set of numbers 2k plus 1 such that k is a whole number. Okay, and this would be the set of numbers 1, 3, 5, dot, dot, dot. Okay, now let's suppose that we're going to take the whole numbers, or the odd numbers rather, sorry, and I'm going to pair those up with the operation of traditional addition. This is not closed. So I don't have to make a big, long, drawn-out proof of it, because anytime we can show an example where something doesn't hold true, then we know that it is not true in general. So if it's not true in general about closure, then it cannot be a closed set with that operation. So what we're going to say is give an example. 3 plus 5 is equal to 8. 8 is not in the set of odd numbers, but 3 and 5 are in the set of odd numbers. And so we've shown that we can take two elements from the set, apply the operation, and we get something that's not in the set, implying that this is not closed. And if it's not closed, it is not a magma. Okay, so I believe we defined what closure means, and I think we get the idea what a magma is. Now we want to go to our next abstract structure, and that is a semigroup. Now, for those of you guys that are computer scientists and you enjoy taking object-oriented languages, you'll see that we have a magma. And what is a magma? It is an object that has a set and has an operation. But when we talk about a semigroup, that is a relationship, because a semigroup is a magma. And so what we might say is this is a subclass of magma. It's a specific instance of magma where there's extra requirements. And so what is a semigroup? Well, a semigroup is effectively, like we said, a magma, except that it adds the requirement, maybe I should do this, adds the requirement of associativity. Okay, it has the requirement of having the associative property. Now, what does the associative property mean? That means if we take A plus B and then we add C to it, that would be the same thing as taking A plus B plus C. So to give a concrete example, just to make sure we're not leaving anybody behind, if we take 2 plus 3 and then add 5, if I do these, and we add 8 maybe, if I take these two things together, I'll get 5 plus 8, and then what would we have? 13? Or if I said 2 plus, but I first grouped these together, 3 plus 8, this will be 13, and I'm adding the 2 to it. Sorry, I made a mishap. This is 11, 11, and this 2 plus 11 will become 13. So notice that we get the same thing. So we can make a more broader argument, but I think everybody understands what the idea of associative property means. So let's take a peek at something. We know that the set of integers under addition is closed. You add two integers, you get another integer back. That's relatively simple. But is it associative? And yeah, it is. It is associative. So when we take integers and we associate them, we get the same value. So in this case, we have closure, and that alone makes it a magma. But we also have the associative property, which means that we also now can identify it as a semigroup. Okay, we have a semigroup. So this is a semigroup. Now, let's consider something else. Let's suppose that we have the integers under the operation of subtraction, traditional subtraction. Well, let's see. Anytime I take two integers and I subtract them, I get another integer back. So we do have closure. So we have closure. Check. So we have a set and an operation, and it is closed. So we have definitely a magma. Okay, but just being a magma doesn't mean a semigroup. If you have a semigroup, then you have a magma. But a magma certainly does not apply a semigroup. So now we need to make sure that it has the associative property. Well, let's see. Can we all agree that 2, 3, and 5 are in the set of integers? Okay. Well, let's see. We have 2 minus 3, and then I'm going to subtract 5. And then I'm going to see if this is going to be the same thing as 2 minus 3 minus 5. Okay, notice that I first over here grouped the 2 and the 3 together, and then subtract the 5. And over here, I'm grouping the 3 and the 5 together, and then the 2. So over here we have a negative 1, and then we're subtracting 5, and then we get negative 6. Okay? Over here we have 2 minus, what is 3 minus 5? That's negative 2. 2 minus negative 2 becomes a positive 4. So notice that these two do not equal, and we have shown one instance where we've taken 3 elements of the set where the associative property does not hold. In order to be associative, it has to hold for all elements in the set, and since we don't have that, that means this fails, the associative property. So we can conclude that we do have a magma, but we do not have a semigroup. And this demonstrates that all semigroups are magmas, but not all magmas are semigroups. Let's take a moment now to consider the monoid. The monoid is the next step. So at this point, we have a magma, which only requires closure. We extend that to create a semigroup. And a semigroup is a magma, except that it's also associative. So closure, associative, and then we extend it further to where we have the monoid. And a monoid, it's required to have an identity. A monoid is required to have an identity. Okay, so let's look at the set of natural numbers under the traditional operation of plus. So, yeah, it does close. If you add 2 numbers in the natural numbers, you get another natural number back, so it is closed. The numbers do associate under addition. However, there's not an identity. So what does an identity mean? I'm going to write out a mathematical expression that discusses that is trying to convey what an identity is, and then I'll try my best to explain the mathematical expression. There exists, so an identity means this. There exists an element E inside of the set such that A plus E is the same thing as E plus A, and that will become equal to A for all A in the set. So let's read this. In order to have an identity, you need to make sure that you understand this. An identity is a unique element. The identity will always be one element in the set if it exists at all. So if it doesn't exist, you don't have a monoid. If you do have a monoid, that means that there is exactly one element inside the set that is the identity. We often identify that element with the letter E. What that means is that if you take any other element in the set and you add it to E, you get the element back. So that's what we're saying. A plus E equals A, E plus A equals A, and that must be true for all A in the set. Now, right now, this seems like, wow, a whole lot of writing, and this is a whole lot of symbols. So this looks like kind of a backward capital E. This upside down A means the word for all, and this bar means such that. So the way we read this is there exists an identity element in S such that A plus E equals A and E plus A equals A for all A in the set. All right, well, let's boil this down. Imagine we have the number 0. Anytime you add 0 to a number, you get that number back. That means that 0 is an additive identity. With respect to multiplicative identity, we have the number 1. Anytime you multiply something by 1, you get the number back. In multiplication, 1 is the only number that behaves that way. Under addition, 0 is the only thing that behaves like an additive identity. So let's take a look. Since we don't have 0 on the natural numbers, there is no additive identity, and so we say this is not a monoid. Not a monoid. However, if we take the set of whole numbers and we look at traditional addition, then notice that 0, the identity element, is basically 0. So that means that for all A in the set of whole numbers, A plus 0 equals 0. A. Okay? So the natural numbers does not have an additive identity, specifically 0. The whole numbers do have 0, and so it has closure. You add two whole numbers together, you get a whole number. When you do they associate? Yes. And it also has an additive identity, so we say this is a monoid. What I would like to do now is I would like to shake up the notion of an operation just a little bit and show that we can define these things in kind of a little bit less straightforward ways like we have with traditional arithmetic. Let's suppose that I say S is the set of numbers 0, 1, 2, 3, and 4. And let's define heart, the operation heart, to be this. Let's see if I can draw a heart. A heart B is my operation, and that will be the same thing as saying this. You take A, you add B to it, and then you take the modulus 5 of it. Now, what does this mod operator means? That means that when you take a number and you divide it, it's the remainder. So let's take a peek at this. I'll erase this in a second. Let's suppose we take the number 9 and we divide it by 5. Well, we have 1 as a quotient with the remainder of 4. And so 9 mod 5 essentially means you take 9, divide by 5, and it's equal to the remainder. This is a very common operation in computer science. You'll see it everywhere. It's very common whenever you're trying to iterate over things and put them into buckets. Super common. So what I'd like to do is I would like to leave it to you to make sure that you understand that modular arithmetic symbol. Maybe mathematicians, they sometimes would write A plus B and then say mod 5. Computer scientists kind of like that percent sign because in most languages, your Java, your C++, and your Python, that percent sign is the modular arithmetic symbol. So I'll leave it at that. Let me erase this. Make sure you understand that before we go further. You can pause the video. So my operation heart, now remember, we don't have an operation heart. We don't have it on a keyboard. We don't do that in math class. I'm just saying operation heart. When you take two elements from the set, S, and you apply the heart operation, it effectively means that you add them together and then do mod 5 in the traditional arithmetic. So let's look at this. Imagine when we were little. Imagine that we were very young. If you remember, you would have like a little card. You had like a little card. And then you had all your numbers down this way, and you had some numbers this way. And when you wanted to look up to see what is 5 times 7, you would look up 5 here, and you would look up 7 here, and where they intersect, they would be the number 35. So when we did 5 times 7, this side, the left operand, you look up here. The right operand, you look up here. Okay? So what I want to do is I want to erase that, and I want to create an operation table that basically mirrors this. Okay? So I'm going to create the numbers 0, 1, 2, 3, and 4. And then I'm going to put 0, 1, 2, 3, and 4 this way. And I'm going to make a grid, and I'm going to define this to be the operation table for heart. Now, obviously, we could write a program to do this. We could write a calculator to do this. But I'm just going to explicitly give all pairwise versions of this. Notice that this is closed. How do I know it's closed? When you look inside this table, notice that every entry in it is from the set 0, 1, 2, 3, 4. So that implies closure. Okay, so we got a magma at the very least. So all of this is basically a magma. Now let's see if it's a semigroup. So we will say we have closure. It is associative. Now if you want to look it up, you could work out a few examples if you're not clear about the associative property, but I believe that you guys will find that it is associative. I'll leave it to you to verify that to yourself if you need it, but this will be associative. Now, what do we have to do to figure out whether or not there is an identity element? Look at the row header right here. Look at the column header right here. And if you see a row and column that mimics the headers, then you must have an identity. Notice that this matches perfectly with the column header, and notice that this matches perfectly with the row header, and so it must be the case that 0 is the identity in this case. So the E, the identity, it is 0 in this case. So we do have closure, we do have associative, and we do have identity, and so what we have is a monoid in this case. Let's suppose that we're going to again have set S, and that's going to be the elements 0, 1, 2, 3, and 4. And now we're going to define maybe diamond, the operation diamond, A diamond B will be this. I know for a fact that anytime I take a mod 5 of an integer, I'm always going to get a value between 0 and 4. So the remainder always has to be 0, 1, 2, 3, 4. So I'm going to go ahead and claim that we do have closure here for sure. Now, if you guys don't mind, I'm going to recreate that same table again. Only this time the arithmetic in the table is going to look a little bit different. See if you can identify an identity element. Now remember what we said. You look at the column header, look at the row header, and see if you see a row and a column that mirrors the header. So it needs to be 0, 1, 2, 3, 4. Notice that we have it right here in the row. We have 0, 1, 2, 3, 4 this way, and we have 0, 1, 2, 3, 4 this way. Now, keep in mind, that's only it matches this header, and it matches the one up there on the column too. So when you look at this, notice that they're both associated with 3 and 3, and they intersect with 3. This will always be a telltale sign of the identity under the operation, assuming that it exists. The identity in this case is 3. So that kind of takes us away from our typical feeling of what? 0 being the additive identity, because that's not the case here. Now let's go back and let's see the properties that we do have. We do have closure. We have closure here. We do have an associative property. I'll leave it to you guys to figure that out, and you pretty much have to kind of convince yourself that it is associative. When you do A diamond B diamond C, and you could regroup the parentheses, you'd find out you always get the same answer. And we also have an identity. So we have all three things. We have S with the diamond operation is a monoid. Up here, same thing. We had S with heart operation, and we have again a monoid. To summarize, in order to be a magma, the operation must be closed on the elements of the set. A magma effectively encapsulates a set and the operation. So we say a magma has a set and a magma has an operation. A semigroup extends a magma by requiring associativity. A monoid extends a semigroup by requiring an identity element. So for computer science students, we say a magma has a set and a magma has an operation. A semigroup extends a magma by also requiring it to have associativity. A monoid extends a semigroup by requiring it to have an identity. Every semigroup is a magma, but not every magma is a semigroup. Every monoid is a semigroup, but not every semigroup is a monoid. Make sure that we understand these relationships, and the more we think about these abstract structures, the more mature of a developer, an engineer, and a mathematician will become, because you start conditioning your mind to start thinking in these terms of being modular and how we can take objects that exist to extend them to create more complex objects. And eventually this will become second nature, and you'll be much more productive in your life, your career, and in your research. So, thank you for watching. I encourage you to leave comments. Let me know what I did right. Let me know what I could do to improve. And I'll see you guys next time.